Hmm.
So, good morning everyone and welcome to our webinar series 2021-22 by organized IEEE MTT-S and IEEE Photonics Society Student Press Chapter Varanasi and IEEE MTT-S Young Professional Community. So today we have the webinar on radio frequency micromachine devices and circuits for microwave to sub-millimeter wave application by Dr. Sukomal Dey, who is currently assistant professor at the Department of Electrical Engineering, Indian Institute of Technology, Palakkad, India. So now I would like to invite Dr. Sumuk Bhattacharya to introduce our speaker, Dr. Sukomal Dey.
Okay, good morning to all of you. So, welcome to the webinar. And let me introduce quickly our speaker over here, Dr. Sukomal Dey. So, Sukomal Dey earned a BTech degree in Electronics and Communication Engineering at the West Bengal University of Technology, Kolkata, India, in 2000, in 2006, an MTech degree in Mechatronics Engineering at the Indian Institute of Engineering, Science and Technology, IIEST, Shibpur, India, an MTech dissertation 1 year at Central Electronics Engineering Research Institute, CDCSIR, Pilani, India, in 2009. Dr. Dey obtained PhD degree from the Center for Advanced Research in Electronics, CARE, Indian Institute of Technology, Delhi, in July 2015. From August 2015 to July 2016, he was working as a project scientist in Industrial Research and Development Center, IIT Delhi. He also worked on a collaborative research project supported by Synergy Microwave Corporation, New Jersey, USA, during the same period. From August 2016 to June 2018, he was working in the Radio Frequency Microsystem Lab, RFML, National Tsinghua University, Taiwan, as a postdoctorate research fellow. Since June 2018, he is working as an assistant professor at Department of Electrical Engineering, IIT Palakkad. Dr. Dey is a recipient of Postgraduate Student Award from the Institute of Smart Structure and System, Bangalore, in 2012. Best Industry Relevant PhD Thesis Award from the Foundation for Innovation in Technology Transfer and Distinction in Doctoral Thesis, both from IIT Delhi 2016. Postdoctoral Fellow Scholarships from the Ministry of Science and Technology, MOST, Taiwan, in 2016 and 17, respectively. Early Career Research Award from Science and Engineering Research Board, ACRB, Government of India, in 2019, and Outstanding Reviewer Award 2019 from Journal of Micromechanics and Microengineering, Institute of Physics. Dr. Dey is felicitated with Emerging Leaders 2020 from the Journal of Micromechanics and Microengineering, Institute of Physics. He has authored more than 70 research papers, one state-of-the-art book, two book chapters, and holds 3 patents. His research interests include RF MEMS microwave to submillimeter wave metamaterial structures and microwave indicator circuits, including antennas. Dr. Dey is a member of IEEE. So, without wasting any further time, so let me just request Dr. Dey to start his presentation.
Thank you very much, Dr. Somak, for the introductions and also for inviting me for this talk. So I am just sharing my presentation. So is my screen is visible?
It's coming, yeah. Yeah, it's completely visible. Can you please click the hide button in the below?
Yeah.
Yeah, it's completely fine.
Okay. So okay. So this I am just changing my slide. So it is also moving, right?
Yeah, it's
Okay.
moving.
Perfect. Thank you. So once again, thank you so much for inviting me in your student branch chapter. And I am Sukomal Dey. So, and today I would like to share some of my thoughts, some of my works that I did in last 10 years on the field of radio frequency micromachining. And I will take you through a journey in this particular thing, that is through a title called radio frequency micromachine devices and circuits for microwave to submillimeter wave applications. So as Dr. Shomak has mentioned that I am currently I'm in IIT Palakkad. So first let me give you a very brief overview about our institutions before I move into the technical part. So this is the bird view of the campus. What is you can see in the leftmost side, it is the map. It is having a total 510 acres area, and right now we are sitting in the our entire work is going on in the transit campus, that is marked in blue circle over here. So, and this is the you can see the nice greeneries over here and other thing. So, and this is the IIT which was one of the new IITs proposed in 2014, and this particular campus was inaugurated on 3rd of August 2015. Then at present, I've been working on primarily four different research topics. That is one that is on which I'm going to discuss with you today. That is RF MEMS, then the metamaterials, then the microwave to terahertz imaging, and different types of substrate integrated structures. So these are the primarily four domains on which my group is working on. And at present, I am having three PhD students and also three BTech students. So those are working on this or working in my group on this particular topic. So with this, let me begin with our today's talk, and that is organized by the IEEE MTT-S and IEEE Photonics Society, IITBHU Varanasi. So in this particular talk, I like my outline will be like this. So first, whenever we are talking about some technology, so say for an example, whenever we are saying a micro machining, that is a MEMS. So we have to know that why we should use that particular technology. So that's why first I will give you some introductions and some motivations of that. Then I will move further to next part, that is switch, then followed by filters. Then I will give you some of the glimpse that how these MEMS are being used in the active circuits, then the antennas. So basically my idea is to cover the entire transceiver architecture, transceiver module, and would like to point out where the MEMS has been used. Okay, so these are my outlines. Now, to begin with, so any kinds of, whenever you are designing or any kinds of radio frequency devices, the first thing is the frequency. So, so whenever we are calling it as a RF MEMS, then first term, that is the RF, which is basically, it represents a frequency, it represents a spectrum, it represents an electromagnetic spectrum. And if you look at the electromagnetic spectrum, it is divided and subdivided into different zones, and each and every zones are having different applications. Like this particular image is showing to you, you can see from left hand side to right hand side, there is an increase in the frequency, and this frequency, and you know that frequency is inversely proportional to the wavelength, so there is a decrease in the wavelength as you are going from left to right. And again, as you are going from the left to right, you can see the applications which is listed over here. That is each and every applications against their frequency. Those are mentioned in the green color. That is mega, giga, tera, peta, exa. So, and each and everywhere you can find different applications. Those are being used. Those are being, some of the devices, those are being commercialized. So this is it has a huge range of applications. So now, to begin with that, so the first motivations I would like to say, that is whenever you are looking, if I take you to the 1980s or 1985s nearly, during that time, the wireless phone, when that era began, that point of time, that point of time, each and every researchers around the globe were thinking that how to reduce the size. If that particular mobile phone, if you have used it, so you can see that these mobile phones are very heavy in nature, and how to reduce the weight of this particular mobile phone. And if you open the set, then you can see there is a So there is a printed circuit board inside that, and in that printed circuit board there is a transceiver module where you can find different kinds of passive circuits, most likely in addition with the active circuits. So the main target is that first target is to how to improve the quality of the passive circuits, because passive circuits inside a transceiver module, that is transmit and receiver sections, though those they are playing a very important role in terms of improvement of the quality factor. So now the problem initially is a high quality factor pose a bottleneck against the miniaturizations. The point here is that you are thinking to improve the quality, and at the same time you are also thinking to how to miniaturize it. If you compare this mobile phone in today's mobile phone, you can see that our mobile phones are very advanced in nature, very sleek in nature. So why it is happening? Because maybe there is a scaling factor. A scaling factor is associated with that, and because of that scaling factor, each and every components are being miniaturized, and how they are being miniaturized, and what technologies are responsible for these miniaturizations. Those are the questions, and those we are trying to answer in this particular talk today. Now, the technology which are adversely used, that is called the micro electromechanical system. So in this particular system, if you look at holistically, it is being divided into different domains based on different engineers. Those are or researchers, those are working on it. If you are a mechanical engineer, you can use this particular technology for microfluidics and pneumatics applications. If you are an electrical or electronics engineer, you would be that you will take the RF MEMS, and then if you RF MEMS and optical MEMS to some extent, and if you are a biologist or a chemist, you can use the biomems. So today's we will be targeting to the RF MEMS. Now in these MEMS, basically they are divided in based on the in different countries. In Europe, they named it microsystem technology. In Japan, they know it is known as micro machines. So now, if you look at the any kinds of technology, whether it is a MEMS, whether it is a CMOS, you know that every technologies are being formed, are being developed based on certain processing method. In MEMS, there are two types of micromachining. One is called bulk micromachining, one is called the surface micromachining. What are the difference between these two? Whenever you are dealing with the bulk micromachining, you are basically taking the substrate into considerations. So what do I mean by that? If you are using a silicon substrate, or if you are using any ceramic substrate, you are basically doing some deep reactive ion etching to get some cavity in the substrate. It is giving you some kind of an additional benefit that I will talk to you later. In surface micromachining, you are not disturbing the substrate, rather you are basically depositing different layer in a layer by layer fashions, or you are basically depositing or sputtering different kinds of layer one after another. This is the primary differences between these two. With this help of this particular technology, a particular micro machining process, you can see one can develop the different types of transmission lines, varactors, switches, filters, and other. And after once you have developed these kind of basic elements, then you are trying to develop it different kinds of passive circuits like filters, phase shifters, and once you have developed it, then you use it in the system to make the complete device. Now, it is basically like in the rightmost side, you can see that there are different applications like mass applications in the mobile phone and the consumer market. You can use this particular technology in the telecommunications, automotive, taste, and high value applications, that is in satellite. So, in addition to that, if you look at the current any super heterodyne type receiver, I know that super heterodyne receiver is very known to every electronics and electrical engineers whenever you are first reading the communications. So in the super heterodyne receiver, if you look at the architecture, you can find there are antennas. Then after getting the signals, you have a switch. Then you have a filters followed by low noise amplifier, again filter. So this is the entire architecture, and finally you are getting in phase and out of phase components. So after the ADC. So now if you see in the blue colored all these blocks, those are already been realized in terms of radio frequency micromachining technology. So the entire system, if you can replace the conventional filters to a mains based filter, or the conventional phase shifter to a mains based phase shifter, so you will see the huge improvement in terms of performance. What are those improvements? That is we are going to see today. So now, whenever you are basically working on a particular technology or working on any particular receiver or transmitter chain, or if you are making any device and if you want to make it switchable, reconfigurable, or tunable, the first important component is the switch. So now, switch is what? So that we will begin with the switch. So the switch means, as you all know, that most of us are aware of the one of the switches that is called the Pin Diode Switch. So the Pin diodes are adversely used in different kinds of applications whenever you are making the circuits, and the switching operations will remain same. Okay, so the pin diode, whenever you are using the pin diodes, you are basically doing the reverse bias mode and the forward bias mode, and you are basically trying to operate the switch based on your need. So here also we are doing the same thing, but in a different ways. What are these things? What are the ways? So now if you look at the any kinds of switch, those are the switches are basically broadly divided into two domains or the two categories. That is shunt switch, series switch. Okay, so if I put it in a very simplest way, one can say that shunt switch is what, which is basically whose main target is to ground the entire signal. So now, and series switch is basically it will pass the signal from input to output. Okay, so now if I compare or if I look at the micromachining technology in terms of shunt perspective, you can see that is in the orange color, you can see the gray color is the substrate, and the orange color, the first layer, you can see there is a ground, then at the center there is a transmission line, and again the ground. So it is a coplanar waveguide. Okay, so the coplanar waveguide transmission line, the first thing what you have to do, you know that to flow the signal, you have to have a path. So the path here is the coplanar waveguide transmission line, and on top of the signal line, you are basically depositing some kind of a dielectric. Then you are depositing some kind of a sacrificial layer. The name is very interesting. Sacrificial layer means that you are depositing some kind of a layer, and at the end of the process, you have to sacrifice the layer or you have to etch out the layer. So now once you have deposited the sacrificial layer, on top of that, you are depositing some, again one metal layer, and at the end of the process, you are basically removing the sacrificial layer. So you are basically creating some kind of a gap between these two conductors. Now, what will happen if you apply a potential with respect to the ground? If you apply the potential between the ground and the signal line, you are basically creating some kind of a potential difference in the middle zone. So now once you are creating a potential difference, then what is happening? If you are applying the electrostatic voltage, this particular beam, it is having some kind of a mechanical force, or it is having something like a restoring force. So now once you are applying or once you are increasing the electrostatic voltage, the restoring force up to a certain time, it is restricting the electrostatic force, or it is keep on fighting with the electrostatic force. And once it reach to a particular voltage, when the electrostatic force, which is absolutely in your hand, when it is more than the restoring force, the entire beam is snapping down. Now, when the entire beam is snapping down means the beam is connecting with the transmission line, and at that point of time, your entire signal will be grounded. So that can be represented with a very simple equivalent circuit model. You can see that from input to output, this is the transmission line, and where when you are applying the voltage, then there is a high increment of the capacitance, and then the entire signal will be grounded. Now, when it is a series switch, what is happening? Just opposite. Whenever you are not applying any voltage, in the shunt switch, when you are not applying the voltage, your signal is going from input to output. When you are applying the voltage, your signal is grounded. In the series switch, just opposite thing happens. See, look at this, the schematic. Whenever you are saying not applying any voltage between this center line with respect to the ground or with respect to this signal line, then you are basically isolating the signal. The entire signal is not passing from input to output. Whenever you are applying the electrostatic voltage, your beam is snapping down, and you can get a nice path from input to output. So this is the way the series switch works. Now, I will give you a nice animations by which I believe that this particular concept will be much more clear to you. Look at this particular figure where it is a fabricated image of a particular switch, and it is a shunt switch, where you can see that this is the RF input line, this is the RF output line, and the side view is showing over here with a schematic where the middle line where the insulator is written, the middle line is the center line. Either side of the middle line, you have a dedicated bias electrode, and they are internally connected. Those can be viewed from the measured from the ACM image over here. Now, what is happening? When you are not applying any voltage, your signal is passing from input to output. You can see the white color arrow, that is it representing the signal flow. Now, when you are applying the voltage, see how are you applying the voltage? This dedicated bias pad with respect to this bridge, we can see. So when you are applying the biasing, then what is happening? Your beam is coming, snapping down, and your entire signal is connected to the ground, and they are grounded. You can see the arrow which represent that it is how the signal is being grounded. So this is the way these kinds of switches are working. Now, why we should select a MEMS switch? It is having couple of advantages as compared with the other conventional solid state devices like pin diodes and FET. So now, if you look at the first point, that is the actuation voltage, which is quite high as compared to the pin diode or FET switch. But at the same time, if you look at the current is nearly equal to 0 or in the microampere range. But in the pin diode, it is basically 3 to 20 milliamps, whereas FET is basically, it is also a very, very less. Now, if you look at, if you have such kind of a value, then obviously, if you take the VI product, that is the power consumptions for the RF MEMS devices, which is very good. But you can, at the same time, you can see the FET is also competing with the MEMS. But if you come to the S parameters, if you come to the loss, that in the loss, the MEMS gives you the best performance. If you see, if you targeting from 1 to 100 gigahertz, if you make a very nice switch, it can give you the loss between 0.05 to 0.2 dB, whereas the FET can give you up to 2.5 dB, which is a quite higher in number. So this is, and in addition to that, if you look at the isolations, it is very good. So these are the advantages if you look at it in terms of isolations, insertion loss, and also in the matching perspective. But switching time is also one of the issue. That is, you may get a little bit of higher in number in terms of switching time. But nowadays, nanosecond switching time switches are also available. So this is the current, in this particular table, you can clearly point out that yes, the MEMS RF MEMS based devices can give substantial improvement in terms of loss or in terms of S parameters. Now, whenever you are making any switch, what is the first target? Whenever you are buying a switch, suppose say for an example, you are designing a tunable filters at maybe at X band of frequency. Your first target, what you used to do if you are using a pin diodes, you are basically look the data sheet and see what are the different values. But what will happen when you are making your own switch? That point of time, you have to make your own data set. At that point of time, you have to make your own data sheet. So now, whenever you are making your own data sheet, needless to say, you have to do a couple of measurements to say that or to fill each and every points. Like if you look at the flow chart, in this flow chart, first you have to do the design, next is the fabrications. After doing the fabrications, you can see in the blue color, it is written measurement stages. So now first you have to do profile measurement. From the profile measurement, you will get to know that because of the residual stress, is there any deformations in the beam or not? Then you have to measure the mechanical resonance frequency. Then you have to see what is the pull-in voltage, that is the actuation voltage, or that is the voltage it takes up. It needs a beam to completely snaps down, and a release voltage, a voltage at which the beam is at a particular voltage when the beam is moving up. Then it is a switching time and release time. Then what is the temperature that it can sustain? Then how much power it can handle? Then what is the linearity performance, like intermodulation distortions, third order intercept point? And after that, you have to check the reliability. So the reliability is a very important parameters, because you don't want your switch to actuate 10 times. Rather, you want your switch to actuate 10 billion times. So now if you are happy with the number of the reliability, you can go to the packaging stage, or else again you have to go back and make your new design. So that is the entire flow on which you are making your own data sheet before you use the switch for certain applications. In the rightmost side, you can see some images like this. The first one that is where you can see the scanning head, optical microscope. This particular instrument is called laser Doppler vibrometer, where you can see the profile, where you can measure the mechanical resonance frequency, where you can measure what is the quality factor of this switch. Then the next one, where you can see LCR meter. This is the where you can see what is your actuation voltage and release voltage. And the bottom figure is very well known to you, where you are measuring the S parameters through a vector network analyzer. So this is the way. These are the different images of some devices, some of the measuring equipments. Now followed by in the so whenever you are defining whatever the measurement procedures I have just mentioned. Now with the measurement procedure, whenever we are making a data sheet, then let us take an example of this particular switch. You can see a switch image is given over here. This particular microscopic image, where you can see an input line and output line, and this is the coplanar waveguide line. In the center line, it is the signal line. Either side of the signal line, there is a ground. Then on the signal line, you are basically keeping the switch, and the switch is cantilever types in nature. Okay, where it is anchored at one point, the other end is free. Now you can see over here, there is a bias line, and then the bias line is going ahead, and then it is having some kind of a twist and turn. That is nothing but the RF choke. Okay, so now you can see a bias pad in the either side of that. So now if you apply the bias, you can see two bias pads, and two bias pad means whenever we are applying the bias, then this particular point, where you can see this particular point, it can touch to the output line, and your signal can pass nicely from input to output. Whenever you are not giving any actuation voltage, you will be getting isolation. So now once you have developed this particular switch, then you have to see what is the mechanical resonance frequency, what is the switching time. You can see the switching time is 118 microsecond. The release time is 78 microsecond. Then what is the actuation voltage? You can see the actuation voltage of this switch. If you see the right, there are two vertical lines are there, blue color. In the rightmost line, it is showing you nearly 40 volt of actuation voltage, and in the leftmost line, it is showing you something like a 24 volt of actuation voltage for the release, that is as the release voltage. Then you can see the S parameters. In the S parameters, in the rightmost side, it is insertion loss. Leftmost side is the return loss and isolations. So the return loss and isolations, isolation graph is showing in the blue color. And you can see that the isolation is close to 17 dB. And this switch is measured from 0 to 20 gigahertz, over which your insertion loss is close to zero point 0.4, or you can say close to 0.5 dB, which is quite a good number if you see 0 to 20 gigahertz, and it is a broadband in nature. It is a broadband in nature. Even if you go to up to 40 gigahertz, you will get your insertion loss up to maximum up to 1 dB. Okay, but isolation, you can see it is close to 17 dB. Isolation is a very important parameters, and matching is a good number, which is close to 25, nearly 20 dB. Now the IIP3, that is the third order intercept point, where you are being means where you test it through some two-tone measurement, where you are giving two frequencies, then you are putting these two frequencies through a power dividers, and you will giving it to the device under test, and you are measuring the IIP3 third order intercept point in a spectrum analyzer. So this is it gives you a very good number, that is 47 dBm. That is if you compare with any other solid state counterparts, you can see that this number is a really good number. Then come to the power handling. You can see that this particular switch can handle till up to 1.5 watt of power. This is the red color showing you the actuation voltage. You can see as you are keep on giving different powers, because of the beam quality, or the quality or the strength of the beam, this power handling is basically the self actuations happens nearly at 1.5 watt of power. So followed by, if you look at the S parameter things that we had discussed if I look at the S parameter things once again, I mean, if I concentrate on the loss over here, you can, whenever you are measure the switch, you have a dedicated equations. Those are very popular equations, and with the help of these equations, you can see what is your RL and C values. Once you get the RL and C values, you can quickly cross check in any circuit simulator that whether you are getting, or whether if you are fit the graph with your measured data, then it is fitting or not. That can be checked very nicely through these equations. Now, as I said, this is the way that you can check the linearity. So you are basically testing some kind of a two-tone method, where you are giving two frequencies. So give it to a power combiners, then you are giving to the device under test, and you see the spectrum in the spectrum analyzer and see what is the third order intercept point. Now, whenever this particular switch was developed, we are not very much happy with the isolation performance, that is 17 dB, because the isolation is very important parameters. So now, is there any methodology by which we can improve the isolations without much effect on the other data? So now we came out with a topology, which is basically a series shunt topology. What is that? You can see in a schematic over here. There's an input line, output line. The input line was having two switches. Now in these two switches, they are grounded. You can easily compare this schematic with this microfabricated image, where there are two switches are being placed. Those are connected with the ground of, and you know that this is the Coplanar waveguide, and in the center line you used one switch, that is the series switch, and these two switches, those are connected to the ground. What is happening? When at one time you are actuating these two switches, those are connected to the ground. So now when you are actuating these two switches, those are connected to the ground, what is happening? The entire signals are grounded. If by any chance there is a signal leakage, those kind of small value of signal cannot pass from input to output, because this switch is in the off state. The switch that is placed on the signal line, the switch which is placed in series, that switch in the off state, so the signal won't pass from input to output. It gives us a substantial improvement in the isolations. You can see the measured data. The isolation is close to 48 dB over the same range of frequency. Whereas the insertion loss, because you are increasing the number of control elements So obviously, initially your insertion loss was 0.5 dB, but here it is just double. So it is close to 1 dB. But up to 20 gigahertz, this 1 dB is still acceptable. If you look at the matching, matching is not adversely affected. The matching is better than 23 dB. So now with the same topology, so with the help of same topology, then we developed one switch matrix. The first switch matrix that we developed, that is the single pole double through switch, where you can see this is the input line. In the either side of the input line, there is a P1 and P2. These are two ports. So now when you are giving the input line, you are activating each and every path. So if you consider this P1 is one of the arm, P2 is one of the other arms. So if you activate this right hand arm, then you can see that when you are getting the signal at the P1, then you are basically doing the same mechanism that I described in the earlier slide. So now in this particular case, what is happening? You can see that the performance is greater than 20 dB. Insertion loss is less than 1.67 dB, which is quite a good number. And the isolation is 39 dB over a range of DC to 20 gigahertz. So this is the performance. The first graph is for input to P1. The next one is input to P2. Now, the same topology are being used for other, like SP40 switch. What is SP40? One input, four outputs. You can see in the first we develop a conventional type switch, where you can see this is the input line and there is a center line, and you can see a shiny four things. Those are the switches. And now though each and every switch is connecting to a different arms. So now all these arms there are four arms. The total there are 5 arms if you consider the input line. So the input line followed by 4 arms. On every 4 arms there are 4 switches. Based on your activations, you are basically routing the signal from input to your referred path. So now after that, whenever we got the experiments, after that we again use the same topology, series shunt topology. You can see high isolation type switch. A zoom image of the series shunt topology is also shown over here, where you can see that every arms are connected with 3 switches. Initially there are 1 switch, but now there are 3 switches. Yes, indeed that you are increasing the number of control elements, but increasing the number of control elements is basically giving you the good performance. If you see in this particular case, your isolation is better than 28 dB, but loss is up to 2 dB. But interesting point to note here is that it is still up to you. If you design the switch matrix in such a way, if you see the center line 143 micron is written over here, this is basically a power divider network. If you really do good electromagnetic simulations, EM simulations, and if you optimize it properly, then you can get rid of high insertion loss. Here you can see the insertion loss is 2 dB up to 60 gigahertz. I repeat, up to 60 gigahertz, this switch gives you maximum insertion loss of close to 2 dB, which is quite a good number. At the same time, the isolation is 28 dB. So now after that, when you develop this particular switch, I will again come back to you once again that why we need this kind of a switching matrix like single pole multi-throw switch. Now, if you look at, I'm presenting 4 block diagrams. The first one, it is basically a direct conversions or the zero IF receiver. So here you can see there is an antenna followed by there is a switching network, and each and every switching networks are connected to a bandpass filter. It is a very, very interesting network. Those are being used currently in mobile phones, currently in any kinds of satellite applications. This kind of it's a bit advanced model of the zero IF receiver, where what are you doing it? You are basically connecting different filters. I repeat, different filters. I mean, the first filter, say for an example, if you consider there are 3 filters over here. First filter is working at 1 to 2 gigahertz, say for an example. Second filter is working at 2 to 3 gigahertz. Third one is maybe working at 3 to 4 gigahertz. So each and every filters are activating based on this particular switch. And these particular switch are being actuated, a particular arm is activated. then the particular filter is connected. So now you are basically, what are you doing? You are basically, it is nothing but, it is an antenna terminated spectrum analyzer. It's more like an antenna terminated spectrum analyzer, where you are working or you are precisely activating different types of switches. In your mobile phone, if you are using any 5G mobile phone, you are at one time, for cellular applications, you need 3.5 gigahertz. For Wi-Fi applications, you need 2.4 gigahertz. So each and every time, whenever you are pressing the button, inside the mobile phone, something is operating. Because of that, you can use the, either if you want to use a Bluetooth, or if you want to use Wi-Fi, or if you want to use any cellular data. So this kind of an operation is basically happening through this multi-switching network. In the next one, you can see it is also a super heterodyne receiver, where there is a filter, where there is a mixer, where there is a VCU, all these are connected. And again, in the third figure, you can see it is called a very interesting setup. It is called the low noise amplifier multiplex module, in short LMM. And here I have written RFFE, stands for radio frequency front end. Now, in this particular third one, what is happening? You are having an antenna, then you are having a filters. After getting the signals to the filter, again you are connecting a switch, and then through the switch the LNA is working. So this is basically a receiving receiver network, and then you are sending it to a complete transceiver. In the third one, you can see that is again radio frequency front end, and then it is basically something like you are basically making some kind of a 2D radio frequency front end array through some antenna that is being used currently in multi-input, multi-output communications. And this, but if you look at all these four figures, and if you take some of the components like phase shifter, switch, oscillators, mixer, so all these components can be replaced or can be made in terms of micromachining technology. So consider this particular slide, that why we need for this kind of a microwave switching network, filters and antenna at the miniaturized stage. So now if you in this slide, I hope that we have the idea that why we need this switching network. Now again, if you look at this particular the block diagram, in this block diagram, again you can see that there is a two antennas connected with a switch. Then they use some kind of a channel selector. So the channel selector means exactly this particular point, whatever I was telling. Channel selector means each and every switches are connected to a filter based on the activations of the switch. Now I am showing you the complete transceiver module, where complete super heterodyne receiver, where different kinds of filters are being used, followed by the switch, and then these mixer filters. So now what is the mixer filters, that we will also see. What is the reconfigurable oscillators? So all these blue colors points, those are already transformed into a micromachining domain. Now coming back to the switch, I said that the single pole multi-through switch plays a very important role. So the single pole multi-through switch, you can see its importance in the making the channel selector. It is having a huge importance if you are making some kind of an antenna terminated spectrum analyzer. So now the need for switching network is very important in current mobile applications or current transceiver applications. So it motivates us to design different kinds of switching networks. Like we started it from SPC 1660 switch, where single pole 6 through you can get, then single pole 7 through, single pole 10 through, 11 through, 12 through, till up to 14 through. Look at the 14 through. It is basically a high quality power divider, where you are basically dividing the power equally. You are giving the signal at the input, coming to the central junctions. In the central junctions, 14 switches are connected to a different path. Based on our shorted positions, I mean, when a particular switch is being activated, the entire signal will go to that particular path from P1 to P14. So, and you can see there is a comparison between all these responses in terms of matching, isolations, insertion loss, and it was being tested up to X band, that is 12 gigahertz, and this is basically giving you some kind of a performance like insertion loss of 1.76 dB. needless to say, these switching networks not only having applications in making a switch bank, but it's also have applications if you are making other microwave devices like phase shifter. So now, what is phase shifter then? Phase shifter, all of us know, but what is the how will you realize the phase shifter in using the micromachining technology? So the realization is possible. So what is phase shifter? The phase shifter is basically giving you a phase shift with respect to your frequency. And if you look at the any kinds of microwave phase shifters, one of the very common phase shifters, that is the reflect line phase shifters, where you use a 3 dB couplers, then you use lots of switches, those are in shunt, and those switches are being placed based on some kind of a space, and that space is defines the phase shift. Now, second category of the phase shifter is the switch line phase shifters, where you connect two arms, one is reference arms, one is delay arms, use some kind of a SPDT switch. First, once you activate the reference arm, take the signal, then you activate the second arm, take the signal. These two arms are having a different length. Based on the different length, you will be having, if you compare the phase between the reference arm and the delay arm, based on the line length difference, you will get some kind of a phase shift. Third category is the loaded line phase shifters, where a line is being loaded with different impedances. So if you are loading the line with different reactances rather, then you can get a different phase shifts. Fourth category is the low pass high pass sections. Again, what are you doing? You are basically adding one low pass and one high pass sections with a SPDT switch in the left and right hand side. And based on the activations of the low pass sections, you can get a phase delay. Based on the activations of the high pass section, you can get a phase advance. Between the delay and advance, you can get a substitute, some kind of a phase shift or differential phase shift. So these are the four different topologies by which one can design the phase shifts. But in one more topologies are also there. I will discuss with you later. So now these are the four topologies, and now in this particular case, we have whenever you are making a phase shifters for a microwave applications, the primarily you need two things. First thing, whenever you are taking a technology which is irrespective of whatever technology you are using, your device should be reliable. Your device should be reliable. I mean, your phase shifter is a very complex device, complicated device, but it has to work till up to 1 billion cycles. Where I am saying phase shifter is a complicated device because in terms of reliability, that you will see it later. But whenever you are making a phase shifter, you are basically doing it what? You are basically creating phase in terms of bitwise fashion. So now the phase shifters are basically a 4-bit phase shifter, 5-bit phase shifters. As you are taking a higher bit of phase shifters, your resolutions will be accurate. You are basically, if you are using in a phased array antenna, so in the phase, if you have a very low LSB, I mean the lowest significant bit. So if you take a 5-bit phase shifter, your LSB is 11.25. That is nothing but 360 degree divided by 2 to the power 5. That is 32. If you divide 360 divided by 32, your LSB is 11.25. So you are basically you can track the enemy radars or enemy vehicles very accurately whenever you are placing it in a phased array antenna. Now, second important point is the reconfigurable. You want your phase shifter to be reconfigurable. If you don't want to work your phase shifter at a particular frequency, you want to make your phase shifter to work at a different frequencies. So that is a very important point. That is, and it has a huge requirement in current architecture. Now, to get these two things, two bullet points, the two methodologies have been adopted. The first one, switch line phase shifter, I discussed. Second category is called the distributed mains transmission line. What happens over here? You have a CPW line. You take the CPW line impedance of 70 ohm. Yes, I repeat, 70 ohm. And then when you take the 70 ohm impedance, you are basically adding some kind of a capacitor. All the blue lines are the capacitors. You are basically loading the line with some capacitor. So whenever you are loading a bridge on top of the signal line, creating a capacitance between this signal line to this blue line, and when you are loading it with a lots of capacitance, what are you doing? Your 70 ohm impedance comes down to, say for an example, 55 ohm. Now, when you are actuating, now once you have loaded the line with lots of varactors, lots of these MEMS bridges, then you are started actuating the bridges. You are having an impedance of 55 ohm. Then you are actuating the switch, increasing the capacitance again. And when you are increasing the capacitance, you are basically again reducing the overall impedance. Say for an example, close to 50 ohm. So between the change of 50 ohm to 55 ohm, you are getting the phase shift. I mean, whenever you are not actuating these bridges, you are taking the signal. Now, when you you started actuating the bridges, you get the signal. Look at the phases between these two signals. One at the non-actuated state, one is the actuated state, and you can see some kind of a differential phase shift between these two states. So this is the way this DMTA distributed MEMS transmission line phase shifter works. Now, the topology that is being targeted for initially, that is the 5-bit phase shifter. The 5-bit phase shifter, as I said, the 5-bit phase shifter, it starts from 11.25, and the topology that is being used over here, that is the switch line topology, where you have a SPDT switch. You can clearly see some kind of a black spot if you look at it very closely. So if you take the 11.25 arm in the here, there you can see two switches. Rather, there are four switches. One switch is SPDT switch in the leftmost side. One switch is the again SPDT switch in the rightmost side. Now the upper arm, you can see all the black spots. Those are the switches. So the 11.25, 22.5, 45, 90, 180 degree. First, you have to develop individual bits. When you are happy with the performance of the individual bits, then you connect them all together, make the complete device, and then you can see this is the RF input, where we are in. If you go through the first line, that is the reference line. The bottom line, that is the delay arm. So now, based on your different actuations positions, you can activate different different phases. Now, in this particular phase shifter works at a narrowband frequency at 17.25 gigahertz, and you can see over a 500 megahertz bandwidth. And this phase shifter gives a 5.48 dB performance. Phase error was 1.45. But the total area of the phase shifter is quite high, 36 millimeter square. But the problem of this phase shifter is the reliability, because we are developing this particular phase shifter for a DRDO applications, and no one is happy by this number of 200 cycle. It means that your device phase shifter works only 200 times. After that, it fails. So then we thought that what is the reasons of this failure? The first reason to understand the reliability of this phase shifter, we have to see where one particular thing, that is, whenever you are testing the reliability of a single switch. So that to begin with the process, we develop the single switch. We are happy with the performance, then only we use the switch for on this particular device. Now, the point here is that whenever you are actuating a single switch, then after doing one actuations, you can call it one reliability for a switch. Now, coming back to the phase shifter. Phase shifter is a device and you are operating in a 5-bit configurations. So now you can call one cycle of reliability when you have tested your device 32 times, because one 5-bit phase shifter gives you the 32 states, 2 to the power 5. So the 30, after doing the operations of the 32 times, then only you can say that yes, my device passed one cycle 32 times of actuations for a 5-bit phase shifter. So that it brings the challenge to us. So that how to reduce, how to improve this performance. So the first thing that we noted that here, if I take the reference signal, so total there are 5 blocks, and 5 blocks there are. Every blocks in the upper half we have one SPDT switch, lower half one SPDT switch. So now it seems to be like that. To activate one arm, we have to activate 10 switches. So the number of control element per phase state plays a very important role. So now our first target is how to reduce the control element. How to reduce the control element? To reduce the control element, it's basically like how to reduce the number of switches. So now that one topology is being proposed over here. You can see here that what we have used for 4 SP40 configurations and 2 SPDT switch, where we model these different phases in such a way that if we activate one arm, you can count it 1, 2, 3, 4, 5, 6. So initially we are having 10 switches. Now to activate one arm, we only have to activate 6 switches. 6 switches needs to be activated. So we have substantially reduced the number of control element per phase state. And with the help of the SP40 switch, the area was also reduced. Initially the area was 36 millimeter square. This area is close to 13 millimeter square, which is quite interesting. After that, we tested the devices, and obviously your S parameter, we have to improve the reliability without compromising the microwave performances or the S parameter performances. You can see the return loss is greater than 22 dB and the insertion loss is 2.65 dB. See, whenever I am saying it, the insertion loss, every time I am saying it average insertion loss, because you have to see the insertion loss from 32 phase states, and after that you have to average it out and give a number to the loss. Now after that, what is happening? We tested the reliability. If this reliability is far better than this, you can see the reliability was tested with respect to the loss and phase error. So now loss and phase error are giving you the reliability. It is giving you something like a 10 million cycles of reliability, which is a quite good number, but still there are some problem. The problem was, so if you look at this particular topology, in this particular topology, again I am writing this particular topology over here. So the previous topology, I said that we used one fine bit. You can see the fine bit is nothing but where you are dealing with the low phase bits like 22.5, 11.25, 33.75, and the coarse bit is the higher digit number like 90 degree, 45, 135, like that. So now in the fine bit and in the coarse bit and then the higher bit. So in this case, we saw that during the operations of the 32 states, the sum of the switches operating multiple times. So the sum of the switches during one 32 times of operations, one single switch are actuated 8 times. Although yes, the switches are not operating 32 times, rather 8 times. But is there any ways by which one can reduce again? One can reduce again the number of switching time or the number of switches per state. Now activations of the switches per state. So one topology was proposed on which we used SP80 switch. There you can see SP80, 2 SP80 and 2 SP40 switches are connected, and accordingly the phase bits are modeled, and that with the help of that, this particular topology can give you a 5-bit phase shifters, and this topology can give you a very compact phase shifter in nature. So that was the topology that was proposed. Then we thought that, is there any way that I can say that over the 32 times of operations, or say if you are dealing a 4-bit phase shifter, 2 to the power 4, that is 16, then over the 16 type of operations, during the time of operations, I can say that my single switch actuations is equivalent to my entire device actuations. Or else, if you test your switch for one time, if you call it one cycle of reliability, during the phase shifter operations, that particular switch also actuated one single time. So now how can you get it? So for an example, so that particular thing was to develop that. Then we developed one 4-bit phase shifter where 4-bit means, as I said, 2 to the power 4, 16. So now we developed one SP16T configurations. So you can see the image, that is a single pole 16 through, where there is a coplanar waveguide line. This coplanar waveguide line is routed throughout these things, and this entire, you can see some cantilever type switches. So each and every switches are connected to a different path from P1 to P16, and whenever you are giving the input signal, signals are going through this CPW line in a circular fashion. Whenever it is getting some shorted path, or whenever a particular switches are connected to the central line to this, then this particular arm is activated. So this is one SP16T configurations was developed. And then what we did, after that, we connected back to back these two SP16T switches. You can see over here. And after that, once we have connected two back-to-back switches, then that point of time, what we did, then this is nothing but a switch line topology, where these switches are connected back to back, and the entire arms are activated. Accordingly, you can get a different phase shift. Now, what is happening over here? Over a complete cycle of 32 times of, 16 times of operations, then your one switch actuated only one time. So if we develop this particular switch, then you tested the reliability. If you can achieve 1 billion cycle of reliability, close your eyes, fabricate the device, then you will definitely get in the phase shifter. If everything goes according to the plan, you can get 1 billion cycle of reliability. So this particular phase shifter was developed at a 20 gigahertz frequency. It was very narrow band in nature, over a 500 megahertz bandwidth, and you can see the loss is 3.47 dB. And you can see the reliability. The reliability performance is also good, and the reliability was checked at 0.1 watt and 0.5 watt with respect to the loss and average phase error, and it operates also at a 50 degree and 85 degree, because this is the industry requirement. In the industry requirement says that your temperature stability should be 85 degrees Celsius. And needless to say, if your switch can handle this 85 degrees Celsius of temperature, it means if your switch can sustain high temperature, automatically it can sustain high power also. But what will happen if you apply high power and high temperature? Then obviously your device won't run for a long time. So if you look at, then after this developing this phase shifter also, we are not happy. We are not happy in the sense that if you look at this particular topology, again, if you say that yes, you are okay, I agree that you reduce the number of control, you reduce the number of switch actuations per state. Yes, you are claiming that one phase state, your switch reliability and phase shifter reliability both are same. But if you look at this particular topology, there are total 32 control elements. So we developed 10 such phase shifters. Out of these 10 phase shifters, only 3 phase shifters worked up to 1 billion cycles. So 7 phase shifters failed in between. So it means that there are total 32 control elements. So now how to reduce these control elements? So again, how to reduce the control elements without compromising the micro performances and targeting a reliability up to 1 billion cycles. So now we thought that yes, we worked on the switch line phase shifters, we worked on the DMTL phase shifters. What if I connect them together? What if I connect them together and make it something like, if I suppose say I have a switching network, in the switching network, you know that in the switch line phase shifters, every arms I have a delay arm and the reference arm, and if I load the delay arm, if I load the reference arm and delay arm, if I load it in the blue line and the red line with lots of varactors, then if I add them together, then what will happen? What will happen? And in the end, we got a really good idea on this. That yes, if you really make these things and it perform very nicely, and then we can have a substantial improvement in terms of overall performance. So, and it came out with a very nice idea. It says that in this case, what are you doing? So let me come to this particular the rightmost figure, where it is the rightmost figure is showing you a 4-bit phase shifter. So here I am showing you the 3-bit and 4-bit phase shifter, but I will explain with respect to the 4-bit phase shifter. So in previous slide, you had seen that whenever we are using a 4-bit phase shifter, we use SP16T switch. We connected back to back to SP16T switch. But here we have used SP8T switch. If you count the number of lines, you can see 1, 2, 3, 4, 5, 6, 7, 8. There are total 8 lines are there, and this is SP8T switch, and there is also a SP8T switch. Those are connected back to back, and in between there is a delay arm. And in the delay arm, if I look at it very closely, in the delay arms are loaded with some varactor. So now here each and every lines, we are actually doing the DMTL operations. Now, what are we doing? Say for an example, you can see 0 degree and 22.5 degree path. Say for an example, you are activating the respective switches. Whenever you are taking the signal from input to output, you are getting the 10 degree phase. That point of time, you are not actuating the varactor. The close view of varactor is shown over here. So this is the varactor. You can now this varactor, once you have started actuating the varactor, you are changing the phase of the signal. Now in this case, one arm is giving you 2 phase data. One arm is giving you 0 degree and 22.5 degree. Then the next arm is giving you the 90 degree, 112.5 degree. So there are total 16 phases are there. And now all the 16 phases are divided into 2. All the 16 phases are divided by 2, and then you are getting 2 phase state from a single arm. So that is quite interesting in nature. And the challenge is what? The challenge is that you have to design the switch. Now here the control elements are where? How many control elements you are having? There is 2 SP8T switch is giving you 16 control elements. Varactor, you don't count it as a control element because it is not giving you the complete actuations. You just need to tune it with some voltage. The beam will never comes down and touch the signal line. Otherwise, your entire signal will be grounded. So check that these varactors are connected to the ground. You just need to give some actuation voltage by which you can get your required phase shift. So by doing these operations, what are you doing it basically? Your challenge is to design the switch and varactor in such a way so that they are having a very close actuation voltage. So it needs some kind of a design. To get the design accuracy, you have to do some kind of a rigorous simulations on by which you can get this data, and these 2 switches almost they are operating on the same voltage, but you can see the voltages at quite a higher level, 110 volt, because it needs so that if your voltage is at higher side means your beam restoring force is very strong. So that if the mechanical force is very strong, that's why it is taking too much voltage, too much electrostatic voltage to come to the snapping positions, to come to the connecting positions. So that gives you a good robustness in your switch. Now, if you look at the S parameter performance, its performance showing you a good number, like a insertion return loss is 12 dB, insertion loss is 5.4 dB, something like that. So now this is to have this particular thing. Again, we are happy with the performance. Then it works up to 1 billion cycles very nicely. And after that, we put it in we made a nice module, okay, in a package form, and we dias the device, put it inside the device, and we check the performance. Over these things, so the few design guidelines on this topology. The first design guidelines is your switch should be robust in nature. Your switching network should be modeled very accurately in an electromagnetic simulator. Then again, the varactor design is a crucial part. Then you have to design the DMTL and delay lines in EM simulators. Then the bias lines, you have to route the bias line in such a way. Then there should be a minimum signal leakage. Then the fabrication process also plays a very important role, followed by whenever it is a contact type switch, so you have to use the well-suited contact material so that at the contact point most of the heat generates. because whenever continuously switches are coming down and moving up, during that process there is a temperature that is being localized at that particular point. So we have to take care of that also. So, and then you have to have a nice measurement setup, accurate measurement setup, so that you can detect the performance of this phase shifter. Now, with this, so just for a quick reference, you can read more for more details. You can read this paper. That in this paper you can see whatever the 5-bit phase shifters and the related reliability analysis are given. This paper is also the paper that I just recently discussed. This paper will give you how to design a very compact, high reliable phase shifters. And also one of the work that I said, the SP16T switch configurations to make a 4-bit phase shifter, all details. The interested reader can read these papers for more information. Now with this, I will present you some of the other things and I will give you some glimpse of the other different devices where the micromachinings are being used. The first thing is the filter. Recently one of the filters were developed. This particular filter, I'm not going into the details of it. As I said, I'll give you the glimpse of this device, how it works. So now this phase shifter, it is a phase shifter which is, sorry, I beg your pardon, this is the filter, bandpass filter. Those are operating at 28 gigahertz. This bandpass filter is tunable in nature. This bandpass filter is reconfigurable in nature. It can tune from 27 to 29 gigahertz. It can track that center frequency tuning. You can see the 27, 28, 29, and all of us know that 28 gigahertz is a very important frequency in current 5G communications. So followed by this particular topology, the proposed topology will also give you some kind of a bandwidth broadening. So you can see the bandwidth, that is, you can see based on the tuning. So now what is all about? You have a switch bank, that is a series switch. Then you have a shunt bank. The number of shunt switches are connected. If you compare this particular circuit schematic with respect to this microscopic image, the first arm is the series switch arm, that is the block 1. The next arm is the block 2, that is the shunt arm. Then you can find a high impedance line. The entire filters are implemented on a CPW, and then you can see the line width is very narrow. That indicates a very high impedance, and that high impedance indicates the inductance. So now you can see the inductance, that is LS, that is being represented with a signal line, with a narrow line. Then again the same topologies are repeated over here. So if you draw a black line, dotted line in the middle, you can see the line of symmetry in the left and right side, or the either side of this line of symmetry, that the same components are being used. And based on the tuning of the shunt arm, you can tune the frequency from 27 to 29, and you can do some fine tuning also. Now based on the tuning of this series, I mean the block 1, you can broad the bandwidth. You can get a substantial improvement on the bandwidth broadening. And you can see this is the measured response. In the measured response, this particular filter was tested. You can see the frequencies are very close by. I am showing you the fine tuning. I'll also show you the coarse tuning. In the fine tuning, you can see you can even tune it from 27.98, 28.18, 28.3. Simultaneously, you can see if you look in the insertion loss, it's very difficult to detect, but you can see in the return loss, it is first of all it's the first order filter. Okay, so this is the first order filter. There is no transmission zero. Only you can get some kind of, you can see from the return loss, you can see there is a peaks over here, and from this peak you can detect what are the FCs. And as I said, this particular filters was developed for a 20 gigahertz application, at 20 gigahertz for 5G applications. And in the first one, it is, you can see this is the tuning. When you are doing it at 27.4 gigahertz, it is 28.3 gigahertz, 29 gigahertz. So this particular thing over the range, if you look at the insertion loss, is close to 1.92 dB, followed by matching of 23.4 dB at 28 gigahertz over a fractional bandwidth of 6.7%, which is a quite good, very good number. So now after that, the filter was the tested, the reliability of this particular filter was also tested, and the more details can be found in this paper. It came into in this year to 2021. In this particular paper, you can get all the informations, all the details. Now with this, let me take you to the next part. That is the filter is not only designed with the help of switch. The filter can also be designed with the help of resonator, right? So now basically, like, whenever you are making a filter, you either without using the switch, you can again resonate the body. You can again resonate the body by making some MEMS based resonator, and it is giving you this kind of a filtering performance. If you look at this is the one block diagram is present over here, and there are different numbers are given. That is if you look at the filter bandwidth with respect to the filter bandwidth, you can see that there is a blocker, there is a ADC, SNR, there is a ENOP. ENOP means equivalent number of bits, then the ADC. So all these are basically, if you look at the filter bandwidth, as you are reducing the filter bandwidth from 35 megahertz to 3.2 megahertz, you can see the ADC power consumption is also reduced. That is a very, very important point, because at the end of any transceiver module is the ADC that is giving you the in phase and out of phase component. That is giving you I and Q. So now the ADC power consumption plays a very important role, so that we have to have the very low bandwidth, that is giving us some kind of a channel selections. So to happen the channel selections, if you have a nice channel select filter which will take a very narrow band frequency, if you achieve that, then you can get up to a number of 0.08. You can get a 0.08 watt of power consumptions. So from the ADC. So now, and simultaneously, ADC ENOP can also be reduced from 12.8 to 2.8. So this is the advantage. What I am showing it to here is that, so the getting a narrowband filter is very, very important. The narrowband filter means your resonator should have a very good quality factor. To get a very good quality factor, so the MEMS micromachine resonator can serve this purpose. Micromachine resonator can give you a very good quality factor. For that, there are different kinds of transaction mechanism. So now the transaction mechanism, one of the transaction mechanism is the piezoelectric transactions. You can see it over here. One transaction mechanism is the capacity based transaction mechanism. So in the piezoelectric based transaction mechanism, you are using some piezo material like aluminum nitride, and all these are filters, and you can see the filtering performance. It is basically giving you, it is working at a 15.3 megahertz for some sensor applications, and there you can see this the insertion loss is around 6 dB. It's quite a higher side, but in this particular case, whenever you're making a capacity based transactions, then you can get a insertion loss of around 3.6 dB. So these are the very important means quality. And look at the quality factor. It is 1500 quality factor, which is quite a good number. Even in MEMS, using MEMS technology, the quality factor of the resonator even reached up to 10,000 or 20,000, which is a huge number. So now after that, even though these particular MEMS-based resonators it is not lying on the megahertz range. Recently, one paper was not recently in 2019. One paper was reported by the Songbin Gong group. He is from basically University of Illinois. This group developed one MEMS-based filter at 4.5 gigahertz, which is for the 5G front end using the micromachine resonators. So the but that part where this can be used at higher frequency also. Even some of the MEMS filters are recently reported even at X band, that is at 10 gigahertz. We'll give you a quick glimpse of how to use the MEMS in oscillators. So just for an overview, oscillators, all of you know what is oscillator. It is a device which has to satisfy a Bartolson criteria, where loop gain has to be greater than 1 unity and the loop phase is 360 degrees. So now whenever you are developing this kind of an oscillators, what is happening? In the forward arm, you have an amplifier. You can use a trans impedance amplifier. In the reverse arm, you have a resonator. If you recall our quartz oscillator, those are being used in the quartz crystal, gives us a very good quality factor, and based on its shape, the quality factor changes. There is a AT card, X card, different cards are available for to define these quartz, to define the quartz crystal. So now, whenever you are developing such kind of an oscillator, the phase noise of the oscillator plays a very important role. And the phase noise defined by the lessons, so the lesson developed this phase noise model, where this phase noise is basically inversely proportional with the square of the quality factor. It means that if from the resonator, if you can achieve a good quality factor, you can substantially improve the phase noise performance. Now, if you look at the phase noise versus offset frequency, you can see that whenever you are getting the high quality factor, it can reduce the close to carrier phase noise. But if you reduce, if your amplifier gives a high power output power, it substantially reduces the far from carrier phase noise. So that is the way we define the oscillators. Now, how to design the oscillator is using MEMS. So what we did over here, you can see the same block, whatever I presented earlier. The upper block is nothing but the trans impedance amplifier. Then the lower block is the resonator. So now in the little bit yellow colored thing it is the fabricated image of the trans impedance amplifier. I am not going into the details of it, but it is this particular amplifier is being developed on a TSMC process of 350 nanometer, and then there are some kind of a block like a transient impedance amplifier followed by variable gain amplifier with an output and loop and output buffer. So now in this case, whenever this amplifier was designed, then the resonator was designed. You can see the resonator microfabricated image, and then you connect them together with some bond wire, and then you can see the phase noise performance. You can see the power output power performance and other thing. Now, this is the way one can use the MEMS in oscillator applications. Then how do you use the MEMS in a mixer applications? Quite interesting. I am showing you that one. This is the mixer microfabricated image of one of the mixer. It's very interesting. Interesting in the sense that if you look at any current architecture, any transceiver architecture, you will get it something like every after the mixer stage there is a filter. Every after the mixer stage there is a band pass filter to get rid of the higher order harmonics. Okay, if you are down converting something, suppose say for an example, you are giving a 2 gigahertz signal, that is the RF, and if you are giving a 1 gigahertz signal at the LO, so you are in the IF stage, you are getting 1 gigahertz signal. 2 minus 1, 1. So now, in addition to the 1 gigahertz signal, you would be having some kind of a higher order components, or you are having some harmonics. So that harmonic has to be reduced through some IF filtering. So now, if you look at the mixer and filter, so can we implement or can we add them together? I mean, we would like to make one device that will give us mixing performance also and the filtering performance also. So we came out with a nice name and we call it as a mixler. Mixer plus filter, mixler. So in mixler, what is happening? You are giving the RF signal, LO is coming from here. See, this particular device is basically identical to the resonate to the filter what I had shown it to earlier. Let me go back and show it to you one more time. See, this is the filter, right? Now, in this filter, where we checked that whether it is possible to do some kind of a down conversions or not. So now but for that, we intentionally make, because filter is a 2-port device, mixer is a 3-port. So we intentionally design this mixer in such a way that it can give us 3-port performance. So I'm not going into the details of it, but see, in that case, you have a RF, LO, and IF. Now you are actuating this mixer and you are getting the mixing performance. The conversion loss is close to 8.55 dB, which is acceptable. I should not say it's good number, but it is acceptable. So now this is in this case. So now one of the important point is that whenever you are making a mixer, you have to see the isolations. Isolation means RF LO isolations, LO IF isolations, RF IF isolations. So now all these stages were checked and the isolations was giving a good number. It is better than 40 dB.
And this is basically brings us a very interesting thing, that it is when you have made it, then it is basically successfully reduce the size in a portable communication system. See, whenever you are basically the compactness has been improved. So there you don't need two components, right? You don't need two components, only one component can be used for mixer and filter both. So now, so you don't need a separate component for mixing and IF filtering. Moreover, it entails added power. It also saves some power consumptions. It saves the power consumptions in terms of a transceiver module. And also there is no questions of the impedance mismatching between one block to other. I mean between mixer to IF filtering. So you are taking care of almost everything and doing the two operations on a single device. So the detailed reference of this, the oscillator that first I presented, the more informations are available in this paper. Interested reader can go through that paper, and the down conversion thing that I just said, the Mixler operations, so that is also available in this paper. So now with this, I have almost come to the last stage, that is the antenna. Antenna is well known that it is developed in a PCB technology. It is developed in the also in the CMOS technology, but also nice antennas were developed in the micromachining technology. But whenever you are using micromachining for the antenna, you should not, your area, plays a very important role. In a micromachining process, if you are making an antenna, better to make it at a highest frequency, because whenever you are making an antenna, some kind of a patch antenna, the patch size is all of us know that patch size is basically a function of frequency. So if you are taking a lower frequency, your patch size will be too big that it will take the entire area, right? Because here, whenever you are taping out from any commercial foundry, the cost plays a very important role. So because of that, it's better if you are designing a micromachine, if you are using the micromachining technology, preferably you design it for a very high frequency. So exactly, we did the same thing. We developed one antenna that is using the same topology. That we developed it at a 60 gigahertz applications. And see, in this antenna, the microfabricated image is shown over here. This antenna is basically one SPDT switches are connected, and each arm, two antennas are there. One is horizontal way connected, one is vertical way. So now, based on the activating of this path of the SPDT switch, the one arm is activated, so that you can get the horizontally polarized signal, or you can get the vertically polarized signal. So this is some kind of a linear polarizations with respect to the horizontal and vertical. You can achieve it with the actuations of the switch. Now, this antenna was operating at a 60 gigahertz frequency, and you can see the radiation patterns and everything. It is quite good. So next antenna was designed at 77 gigahertz for automotive radar applications, because all are these 60 gigahertz, 77 gigahertz, 60 gigahertz generally used at a short distance communications, so secure communications. 77 gigahertz is also used for a automotive radar applications very widely. So here, what we did basically, here we are doing some kind of a reconfigurable, and reconfigurations in the antennas can be made in, you can make a reconfigurable in terms of frequency, you can make reconfigurable in terms of pattern reconfigurable, you can make it polarizations reconfigurable. So there are different ways you can reconfigure an antenna. So here we have made it as a polarization reconfigurable. So there it is basically like we connected these two arms at one time, one diagonal arms are activated, and on other time, one other diagonal arms are activated. When one diagonal arms are activated, there are, you can see on the patch there are 4 switches. I'm talking about the diagonal arm. Don't consider the arm, the switches, those are side by side. So if you activate the diagonal, two opposite switches, then your antenna will resonate, and it will give you the left-handed circularly polarized. When other two arms are activated, or other two switches are at opposite switches are activated, then you can get the right-handed circularly polarized. So you can see the radiation patterns of these antennas. So this is, and this particular antenna, you can see it from the performance, it works it at close to 77 gigahertz. Now with this, I would like to close it to give you some kind of a current state-of-the-art things those are going on in MEMS at a terahertz domain. So in the terahertz domain, so very recently one of the one paper not very recently. It was the beginning of their journey, where one of our very renowned Indian, that is Dr. Gautam Chattopadhyay, was also involved in this particular research. So with the Joachim Overhammer from the Joachim Overhammer is from the KTH Sweden. So this particular group was developed, and they have been developing different kinds of micromachine waveguide based switches using a 3D micromachining technique, extremely sophisticated technique. So where the switch they are making using a 3D micromachining. So you can consider, you can recall, or you can consider it in terms of a 3D printing technology also, but in a micromachining scale. So what they have done it, they have made one waveguide switch. So this waveguide based switch, and you can see in the middle there is, I will show you the block diagram. This is the schematic. There you can find there is some cantilevers are connected. The yellow color, gray colors things are there. So now I will show you the microscopic image of their device. So see, this is the reconfigurable surface, and this is nothing but an waveguide. This is nothing but a waveguide. You can see there is some vertical lines. You can see. I beg your pardon if it's difficult for you to see this figure, but if you look at it over here, so you can see the yellow color and gray color. These are two bars. Okay. So now what is happening? And these two bars are controlled through some comb actuator. You can see left hand side is a comb actuator. It is basically gives you some kind of a lateral movement. So now using a lateral movement based on some actuations, so every switches are. So now what is happening? If you consider they are making a rectangular waveguide, they are trying to activate the TE10 mode of operations. That is the dominant mode. What they are doing it at one time, whenever there is not actuation voltage, signals are propagating very nicely through this waveguide. Whenever you would like to block the signal, you connect this arm. You just it is like a string. You just pull it, and then the entire these cantilever, so-called cantilever beams are connected through this, and the entire signal will be blocked. So now you are basically, when this entire signal is blocked, you are basically adding some vertical rods. You are adding some vertical rod and these are conductor. So now your waveguide operations of the TE10 mode, it is completely disturbed. You are not going to get one half cycle of operations. You are not going to get one half cycle of operations, and your entire electromagnetic wave phenomena, your excitations of the TE10 mode was completely shorted, completely blocked. So now this is the very nice configurations, and see it works at a 500 to 700, 750 gigahertz. Because only waveguide can give us this kind of performance. So now see the insertion loss and matching. You can see I am just showing you their data. So it's an excellent performances are given. Now these particular groups, nevertheless, they also developed this kind of a switch to 2000, right from the 2016 to 17 till up to today, till up to 2021. They have been developing switch, filters, phase shifters, antennas, all these with the help of this 3D micromachining technology. Now after that, even in the current days, so the frequency selective surface are also a very widely used topic. So if FSS is basically, I would not say it's a metamaterial based structure. I can consider FSS, frequency selective surface, is one of the subset of the metamaterial, you can call it, because some of the property matches. So this is the image, this is the photograph I am showing you. It is basically a frequency selective surface where there is a lots of cantilevers are connected, and with the help of this cantilever beam, one can make it is a reconfigurable frequency selective surface. So the reconfigurations can be made very nicely, and for the measurement, the setup that they used, I am taking a source that this particular paper was available in IMS 2016. If you are interested, you can look at this paper. So now to measure these things, you have to measure it in a TDS, that is the time domain spectroscopy, or you can use it, or you can measure it in a high-end VNA. But the important thing to note here, what is the reason why I put this? The reason is that the fine tuning of this entire surface, which is quite interesting to me. You can see between these close to 1.05, close to 1.05 to 1.1, in between that, they can almost track almost all the frequencies. So almost all the frequencies can be tracked. So it gives us a very fine tuning. If you really make it, if you really fabricate such structures, if you really place the cantilever beam in a periodic manner, just to activate or just to play with the capacitance, just to play with the inductance, and as well as just to play with the entire surface, entire frequency selective surface, so that you can get a nice operations even at terahertz range using this micromachining technology. So now with this, I am concluding my talk. And before I conclude, I would like to acknowledge my PhD supervisor. I did PhD from Delhi, so and under the supervision of Professor Shivan Kaul. And also I would like to thank Professor Ajay Poddar, with whom I worked after my PhD. And I would also like to thank Professor Shengxiang Li from NTHU Taiwan, where I worked with him for 2 years, and I got an opportunity to learn some of the RF active circuits. And in the end, I would like to thank my sponsor, who is that is the Science and Engineering Research Board. With the help of the Science and Engineering Research Board, we developed RF anechoic chamber and an MMS laboratory at IIT Palakkad. And whatever the things I just shared, most of the informations are available in this book. So this book particularly talking about how to improve the reliability, how to design switches, different kinds of high-end switching networks, different kinds of phase shifters, tunable phase shifters, reconfigurable phase shifters, and other. And with this, I would like to thank the IEEE MTT-S and IEEE Photonics Society, Indian Institute of Technology, Varanasi. And my special thanks goes to Dr. Somok Bhattacharya, who is a very good friend of mine and who is currently as an assistant professor in Department of Electronics Engineering, IIT Varanasi. And I would like to thank all the speakers for I took almost more than 1.5 hours, so I'm sorry for that. And I would like to thank you for your attentions. And also, if you have any questions, please feel free to ask me. Thank you so much.
Okay. Thank you, Dr. Dey. It's really a wonderful talk. First of all, let me tell you. So there are few questions are there in the chat box. So should I read, and you can will you like to take it?
Please.
Yeah. So one of them is asking, sir, how far can we go by using the micromachining techniques? Can we fabricate devices of dimensions with micrometers or nanometers in India?
Yeah. So it's a very good question. So yes, the obvious answer is yes. You can fabricate micron scale in India, because some of the switches, whenever we are proposing any switch, the first thing what we did, we developed in our lab in care. So I'm just sharing my journey. So and then after that, once we are, if I was having some problem during the development, then we developed few of the switches from Sita that is in Bangalore. And and even some of the switches was also developed in IIC. So now, why I'm saying that, the Indians organization like IIC Bangalore, even some of the one lab microelectronics lab here, then ACL Chandigarh. So all these labs can develop, or they are developing these MEMS-based devices in micron scale. Okay. Now, if I come to the nano scale, sorry, I missed IIT Bombay. So IIT Bombay, I missed TIFR Bombay also. Just I am telling you, these are the names though where you can, these kind of switches are being developed. And now if I come to the next part of your question, that is nanometer. Yes, there are nanometer range. There are different research are going on, and some of the nano rods, or the nano rods by carbon nano rods are also developed by IIT Bombay from the even Professor Professor, if I'm not mistaken, Professor Ram Gopal Rao developed different kinds of nanoscale devices. Then CD Pilani, they are also developed good nanometer scale devices. So these are the different zone where you can contact if you are really wanted to fabricate some of your structure in micron and nanoscale.
Okay, thank you very much for this one. And I can see some other questions are there from Dr. Ayan Chatterjee. So, Dr. Ayan Chatterjee, are you here? Hello, Dr.
Hello.
Chatterjee.
Hello.
Yeah. Please go ahead. Yeah.
Yes, sir. Sir, I have two questions actually. I want to ask that we generally develop the antennas in microwave frequency range, but we do not get the opportunity to integrate those antennas with the filters or power dividers or the phase shifters because there are lack of collaboration in the laboratories because the same field researchers are not available. So how can you make sure that our developed antennas can be actually they will work if we integrate with the filters or power dividers?
Yeah, it's a very good questions once again. So that I think that this particular question lies irrespective of you are using micromachining technology or any PCB technology. So if you are making your circuit, so this kind it is basically like a impedance matching issue. So for to solve this problem, so whenever you are making your antenna, that point of time, first thing that always we have to see that yes, the loss, the matching. So now once you are satisfied with the matching, then simultaneously you after the antenna, the next stage is the filter. So now the point here is that you can always uh, try to match, or whenever you are designing the antenna, you can always design a filter also along with that. So or else there is a, I can't give you any straight cut answer for that. Basically like uh, so it's all about the design, because whenever we are designing any kind of devices like an antenna filters, always we take input and output impedance of 50 ohm. Now the questions can be something like that. If you are designing an active circuits, so most of the active circuits like LNAs or power amplifier, in some of the cases it may so happen that your output impedance is exactly not 50 ohm. So in that case, you have to whenever if someone is designing a filter after a low noise amplifier, then he has to know the output impedance of your amplifier. Accordingly, he can design the matching network so that his filter can be placed. So it is basically this particular, whenever you are making an entire transceiver chain, at least up to a certain point of time, we have to work closely. Suppose person A is designing an antenna, person B is designing a filter, person C is designing the switching network. So like that, you have to collect the data from each and individual, and you have to make the system level. Or it's better at least up to an RF front end if you can make it. If you can if you can assign someone to develop the RF front end, like a filter, like an antenna, filter, and the switch, if possible, or antenna and filter. Or in you know that in recent literatures, lots of the antennas are coming with a filtering application. They call it as a filter. So basically like because of the question that exactly works, so these because of that issue they are moving into that particular design. So sorry, I can give you a very straight cut solution or the straight cut answer to this problem, because this particular is not a problem, it's a design challenge, and it is available irrespective of whatever technology you are using. I don't know, I give you the
Yes, sir. Yes,
yeah.
sir.
Yeah,
I
yeah,
have
it's a
got.
good
Yes, sir.
understanding.
I have got some suggestion. Thank you, sir. And I have one more question. That is, sir, I have seen in today's presentation that you have designed on bandpass filter at this 5G for 5G application that
Yes,
was
yes,
in the 28 gigahertz. So,
yes,
sir, my question is, we see some of the literature, some of the research papers, they are also presenting at sub 6 gigahertz.
yes.
So, as 5G has not come to our country till now, so my question is it appropriate that in sub 6 gigahertz also we can design the antennas or different components, and we can claim that they are also for 5G applications?
I mean, yeah. Means if I understood it correctly, your question is that that your question lies on the sub 6 gigahertz, right?
Yes,
I mean,
if I design for sub 6 gigahertz, because I do not have the facilities at above 28 gigahertz, so can I claim that that is also for 5G application?
absolutely, yes, indeed. So the sub 6 gigahertz, basically in the sub 6 gigahertz, the 5G frequency is the 3.5 gigahertz. I mean, in the cellular, if you call it a cellular, Wi-Fi is still at 2.4. So the 3.5 gigahertz is the frequency where the 5G communication is going on. So you can even, I'm telling you, you can even spend almost coming 2 years or 3 years time on working on the sub 6 gigahertz. We can do lots of things on the even on the sub 6 gigahertz. You don't need to go beyond 6 gigahertz. You can make the filter, you can make the antenna, you can make the amplifier, oscillator, mixer, whatever at 3.5 gigahertz. Okay,
Okay,
so
thank you,
that is
sir.
absolutely possible. So now the point, now let me tell you one more thing.
Yes, sir.
If you take, you can consider 3.5 gigahertz. So what are the frequency you can consider? You can consider 3.5 gigahertz. You can consider 2.4 and 5 gigahertz. That is for the Wi-Fi. 2.4 and 5. So I'm telling you, directly giving you three frequencies. That is 3.5, 2.4, and 5 gigahertz. So you can build your different devices on these particular frequencies.
Yes, sir. Yes, sir. Thank you, sir.
Have I made you clear?
Yes, sir. Definitely. Thank you, sir, for this informative session. It was a really wonderful lecture. We got so many things to learn from this
Thank you so
lecture.
much.
Thank you,
Thank
sir.
you so much.
Another question is there from Dr. Soumojit C. So, Dr. Soumojit, are you here? Hello, Dr. Soumojit. Yeah,
Yes, sir. Good afternoon, sir.
yeah. Please go ahead.
Hello.
Yeah, please go ahead.
Sir, actually, that has shown some of the this capacitor, the director was loaded in that structure. Sir, I could not understand how one capacitive loading can reduce the impedance of the circuit. I could not relate it. Can sir please explain?
So the capacitive loading can reduce the impedance, you are saying?
Yes.
How the capacitive loading? Okay. Okay. So let me go back to the slide, then probably. Yeah. So, okay. So what I was telling is that, your name is Soumojit? Soumojit?
Yeah, yeah.
Yeah, Soumojit.
Yes.
So what you can do here, if you look at these particular, consider at one stage where these, where you don't have these varactors. You design the coplanar waveguide in such a way that the impedance is 75 ohm. Now, after that, when you are loading or when you are adding this capacitor, what is happening? Whenever you are adding the capacitor, you are basically you're increasing the capacitance on the line, on the center line, on the RF line, on the signal line. You are increasing the capacitance. So whenever you are increasing the capacitance, what happens? Whenever you are increasing the capacitance, your initially whatever the impedance we are having, that is 75 ohm, that impedance was reduced to, because the capacitance, overall line capacitance has been increased, so the impedance have reduced to, say for an example, 75 ohm to 60 ohm. Now,
Okay, sir. You are talking about AC resistance, right?
sorry,
AC
I didn't.
resistance. That sir, you are
Yes,
talking about the AC resistance actually
yes,
because
absolutely.
of this
So
capacity. Okay. Yeah.
correct, absolutely correct. So because of the capacitive coupling, so the capacitance is basically what it is doing. It is basically the entire this structure, the distributed mains transmission line. Entire this structure is basically, it is a purely impedance matching network. You have to play with the impedance throughout the day. So initially, you are, as I said, you have 75 ohm, load the line with 75 comes down to 60 ohm. Then now, once you are having 60 ohm, started your operations. At 60 ohm, you have a one phase state, that is phi 1. When you actuated the switch, then 60 ohm again reduced to 50 ohm. Okay, your main target is to, at the end of the day, comes to a 50 ohm. Okay, just to improve the loss. So 60 ohm comes to 50 ohm. So over these 60 to 50 ohm impedance variations will give you the change in the phase state. So while you are continuously operating these bridges, you are basically playing with the phase velocity. So that phase velocity finally brings you the differential phase shift. Okay, that is omega by beta. Okay, that beta is basically giving you the phase shift. Are you getting my point? Have I made you clear or not?
Yes, sir. I got your point. Okay. Yeah, I thought that it is simply I was trying to simplify these things actually, oversimplify actually. Okay, now I got your concept.
Yeah, yeah. So you can, if you look at this particular thing, one more just to I would like to show you something. If you look, if you can see the first block, that is 0 degree, 45 degree. Can you see that the 3-bit phase shifter, the first one? So there you can see, if you look at the coplanar waveguide line, you can see this, the entire line if it is coming like this, and after reaching a certain point, so there is a change in the impedance. You can see that the gap is more on the line.
Yeah.
So gap
With
is
this
more.
also.
Yeah, keeping the line width same, if you are increasing the gap, okay, so then you are basically, what are you doing? You are increasing the impedance, your coplanar waveguide, so CPW impedance will be more. Okay, so now if you if you add the character, then again the overall, the collective impedance will again be reduced. So that is the overall story. So do I make
Okay,
myself
sir.
clear
Thank you,
to
sir.
you? Yeah.
Yes.
Thank you.
Okay, thank you.
So thank you, Dr. Dey, for this nice presentation once again. If any kind of quick questions from others, so these are the questions I have read out from chat box. If any one of you have, we can take another 1 or 2 quick questions. Any one of you want to have ask any question, please go ahead. Maybe one quick question from any one of you can go ahead.
Hello.
Hello, yeah, Dipti, please.
Sir, actually, I want to know, sir, because these devices are the designing is little bit complex. Then how it will affect the thermal after the assembly, sir? Means in which parameters after the assembly, because there are so many components, there are some active devices is there, so passive devices is there, sir. So how it will control the temperature, sir? Means up to how much temperature we can after we giving some supply, input supply, means it is how much temperature it will affect, sir? Thermal effect, sir, I want to know, sir.
Okay, interesting question. So the thermal effect. So the first of all, if you are making any devices for industry applications, in most of the cases, the industry will give you a temperature zone over which your device should work. That zone is minus 40 degrees Celsius to plus 85 degrees Celsius. Minus 40 degree to plus 85 degrees Celsius. So that is the temperature zone over which your device should, that is the temperature your device should withstand. Now the point here is that whenever you are making such device, so I'll go back to one particular thing so that I can tell you much better. Now, say for an example, once you have designed it, then you have to check the temperature stability. I mean, you might have seen some of my graphs, some of the results that was tested at at different temperature, like I showed 50 degree, 85, yeah, 50 degree, 85 degrees Celsius. So the point here is that whenever we are checking the temperature stability, that point of time, first we checked it, we keep it on a hot plate. Okay, so we keep it in a hot plate and the temperature was controlled. And then when controlling the temperature is basically comes, it started with at a room temperature, then you will keep on increasing the temperature, keeping the power level low. Okay, so your power level should be at 0.1 watt or maybe below than that. Okay, so take the low power level, keep on increasing the temperature, and do your S parameter operations as if you are testing it inside the VNA. Okay, so now you take the reading of the loss. You can see my rightmost side, the average loss. So so the graph. So now you started the frequencies, started at 25 degrees Celsius. You won't find much difference till up to 30 or 35 degree. Some 40 degree and onwards, some of the changes may occur. So now once you are keep on increasing the temperature, as simultaneously you are noting down the data. Okay, so data of the loss. Now, if throughout these operations, keep the power level at lower side. Now, when you are completely satisfied with the temperature of 85 degrees Celsius, then you can be little bit of greedy. You can increase the power level from 0.1 to 0.2 to 0.3 like that, and change it. And most of the cases, the industry want up to 1 watt of power for these kind of devices. So minimum one out of power. So now then you change it the power, and also you also at 50 degrees Celsius, again you do some power variation, test it 0.1, 0.2, 0.3 like that, and see the operations. This is the way you can check your device at a different temperatures and also with a different power. So now
Means we have to check the power, sir.
See, absolutely correct. So the point here is that power is basically is a function of temperature.
Yes, sir.
Right? So now the point here is that if you are satisfied with the 85 degrees Celsius of temperature, then if your device can sustain 85 degrees Celsius temperature, then obviously at 25 degrees Celsius, this device can work with 1 watt of power. At 25 degree or at room temperature, the device can work with 1 watt of power very nicely.
Okay, sir.
So just as an example. So
Yeah.
So this is the thing basically. So the more details, the temperature thing also it was mentioned. If you have some time, you can go through this paper. It was published in 2015 in TMTT. So there these particular things were mentioned. How the temperatures are affecting on the device performance. Okay. So the more details can be found in this.
Doctor, I have a question, which I don't know. Means what is the typical power handling capability of these devices?
So, if you ask me in the current time, it has already reached up to 5 watt of power.
Oh, it's huge. Yeah.
4 to 5 watt of power on a conventional Coplanar, I mean CPW or CPW version. So, but if you use it as 3D micromachining, if it is a waveguide, then you can substantially improve the power.
Okay.
Sir, in VNA it is up to means 1 watt or something. So it is taking the power from VNA, sir.
Yeah. No. You cannot check the power handling capability using a VNA. You have to use traveling wave amplifier.
Yeah.
You have to use traveling wave amplifier for that. Okay. So or you do if somebody has a very good power amplifier that can produce 5 watt or 2 to 3 watt of power, because 1 watt or 2 watt of power amplifiers are available in the market. You can buy it and check it. Okay. Don't test it. Don't check it. Don't test it using VNA.
Okay, sir.
In a power level, it's not always very much reliable. Okay. So better to use it to check the power. You can better to use this preferably. I would rather say traveling wave amplifier, but you can always check it using power amplifier.
In fact, doctor, they can tell it better than me. I believe that in VNA, that whatever the power they are providing for measuring S parameters, that is of the order of dBm. So a few milliwatts only.
Yeah.
Correct. Absolutely correct. Absolutely.
So maybe one quick question from anyone else. Maybe one quick question from anyone else. I can allow one more question, not more than that. Okay, so if there is no more questions, so let's thank the speaker, Dr. Sukomal Dey, once again for providing very good time to us and for enlightening us regarding this discussion on MEMS device for high frequency application. It is really beautiful. So I can see that Professor Raghavan is present among us as audience. Sir, please.
I just want to say hello to my dear friend Sukomal Dey, Dr. Sukomal Dey.
Oh, hello, sir. Hello, hello. Oh, I'm so happy that
Today
you are
only
here.
I come to know that you are the second author of that book. Once Dr. Kaul has sent the details, but I feel very proud that you are the second author. Very happy to join with you through my friend, another friend, Dr. Shomuk.
I'm so happy that you are there, and you are listening my work, and I'm so happy, sir. Thank you so much for
Your
attending my
talk was
talk.
so professional.
So nice of you, sir. Thank you so
Thanks
much.
a lot to you as well as Dr. Somak.
Thank you, sir.
Okay.
Okay, so as there is no more questions, so let's stop over here and thank you everyone for attending the same. Before we leave, just let me just request all of you that in the email which we have circulated, that where the link was given, that our Facebook page link as well as our YouTube channel link has been provided. So please subscribe those for future updates. And the recorded version of the talk will be available as very soon, maybe within a day or so. And so please tune to that channel to listen to us. Yeah.
And
So
if you have any further any questions, you can always write to me.
yeah,
My email ID
yeah.
is given. And I just wanted to say that. Sorry to interrupt you.
No, it's okay, it's okay, it's okay, it's okay.
Okay. And
So,
I'm really, once again, I'm sorry that I took a bit more time.
no, it was wonderful and we really enjoyed it. That's why people didn't get bored. Yeah.
Thank you so much for your kind attention.
Yeah. Thank you, Dr. Dey, once again, and yeah, so thanks everyone else also. Thank you.
Thank you, Dr. Somak, once again for giving me this opportunity to share my thoughts and deeds with you and your team. So thank you so much.
Yeah. Thank you.
Have a nice day.
Thanks.